This is your second lecture for Chapter 9, and we're going to continue on with valence bond theory, and then after that is molecular orbital theory, and that will do it for this chapter. Okay, so when last we left, we were looking at VSEPR theory, valence shell electron pair repulsion theory, and it talks all about the whole basis of that is that the areas of electrons around a central atom are pushing each other apart as much as they can. So they find optimal arrangements. And after the advent of VSEPR theory, experimental evidence showed that a lot of it was really, really correct. So scientists needed to find a way to explain better why the shapes that we've determined were correct were happening. And so what they came up with was valence bond theory. And the idea about valence bond theory is that it's all concerned with direct overlap of orbitals forms bonds. Okay? Covalent bonds. Right? That's the main idea with valence bond theory. And so if we take the ideas from VSEPR, and I'm going to use a lot of images in this particular section of this lecture because my drawings they would be painful for you to try and decipher. So if I take this idea about overlapping orbitals and I apply it to VSEPR model of methane, CH4, what it does is it is all of the p orbitals. So taking a look down here, these are the p orbitals of carbon, and they exist in the x, y, and z directions, right? And so if VSEPR is correct, completely correct, then these three orbitals, these three p orbitals, will orient themselves as far apart as possible, just like it's shown in this particular drawing. So if I overlap my hydrogen 1s, so these are all hydrogen 1s orbitals, right? Because that's all hydrogen has to play with, right? And if the hydrogen 1s overlaps with p orbitals directly, like we see here, what I end up with is something that will have 90-degree bond angles, okay? And that's not what they determined experimentally. We know that CH4 makes a tetrahedral thing, and we get 109.5-degree bond angles. So there's some conflict here, okay? So they were trying to explain this, and so they figured, well, let's try to combine atomic orbitals, okay? So if I have a 2s orbital from my carbon, so this is my orbitals from carbon, and if I arrange them in order of energy, so looking at the energy here on the left, the energy arrow is going up, so higher up is higher energy. My 2s is lower in energy, and my 2p is higher in energy. And my carbon has got 4 valence electrons, so 1, 2, 3, and 4. Okay, if I combine those 2s and those 2p orbitals, what I can do is get 4 orbitals, each with an electron. Okay, and they'll be slightly lower in energy. Slightly lower in energy than the p. Okay, so what we get is if I have 3 p's and 1 s orbital, if I combine those, what I get is s, p, 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 or what we refer to as sp3 hybridization. Hybrid. Okay, so if I take 4 atomic orbitals, so over here I have 4 atomic orbitals, okay, I should get 4 hybrid orbitals. Right? So I'll have 1, 2, 3, 4 sp3s. Okay, and then again, that comes from combining one s orbital and 3 p orbitals. Okay, so I get these hybrid orbitals, and what they do is, and this is showing the same thing, is what they do is they combine, right? So if I take my 1s orbital and I combine it with 3 p orbitals, what it does is it alters the shape and orientation of all 4 of those orbitals. So now I have 4 hybrid orbitals, 4 hybridized orbitals that have slightly different shape and orientation. And when I put those all together, ta-da, we are left with tetrahedral geometry. Okay, so let's take a look at how we can look at the molecular shapes of different things. Okay, so determining the hybridization, okay, that's what we want to do. We want to determine hybridization around a central atom or any particular atom. Okay, so just like we did in the previous section, we were determining geometries about a central atom. I'm going to use similar tactics to determine hybridization. Okay, so with things that have a linear shape, what you want to do is count the areas on the central atom, just like you did when you were determining geometry. So with my carbon dioxide here that I'm showing is a linear molecule. It has 2 electron areas, no lone pairs. So I've got these 2 areas, right? 2 areas around the central atom. You're going to combine an S and a P. So you're left with an SP hybrid. Okay, so if I were to label this, I would label that central atom as SP hybrid, okay? Because I've only got 2 areas, an S and a P. All right, so to sort of look at how that is arranged, as far as my energy diagram, right? Talking about carbon there, he's got his 4 valence electrons. And I'm going to take and combine 1s and 1p orbital. Okay, so we'll end up with 1, 2, 3, 4. Okay, and what we have up here on the top right, these are unhybridized p orbitals. Okay, so there's 2 p orbitals that have electrons that are not going to participate in anything. Okay, at least not directly. And a little bit later on, we'll look at some diagrams which will help to illustrate this better. Okay, so I've got 2 hybrid orbitals, 2 sp hybrids, doing all my bonding in carbon dioxide. So let's look at our next type of shape, which was trigonal planar shapes. Right? So again, we're going to take a look at how many areas of electrons there are around my central atom. There are 3. So I've got 1, 2, 3. So 3 areas. So I've got an S, a P, and a P. Okay, there's 3 things there to go with 3 areas. So we'll call this an sp2 hybrid. Right? And if I were to label, I would call that carbon sp2 hybridized. Right? So looking again at our arrangement of electrons from that carbon, when I hybridize them, the hybrid orbitals have slightly less energy than the p orbitals originally did. Right? And again, up here in the upper right, this is an unhybridized, hybridized p orbital. Okay, so sp has 2 unhybridized p orbitals. sp2 has 1 unhybridized p orbital. So let's take a look at tetrahedral shapes. 4 areas, 1, 2, 3, 4. 4 areas, S plus P plus P plus P. sp3 hybridized. Okay, so an S and 3 P's, that gives me sp3. So I would label that nitrogen as sp3 hybridized. Okay, so our nitrogen's got 1, 2, 3, 4, 5. And I'm going to put all 5 of those in 4 new sp3 hybrid orbitals. 1, 2, 3, 4, 5. Okay. Notice that I've used up all my p orbitals, so I don't have any unhybridized p's. No unhybridized p's. Okay. So the takeaway message here is count the areas of electrons, and that many areas will tell you what the hybridization about a particular atom is. Okay, so taking a look at how that sort of plays out. So methane is our CH4. And if I were to draw a Lewis structure for CH4, it would come out like this. And if we wanted to know what the hybridization was, we would say there's 1, 2, 3, 4 areas. We would say S, P, P, P. 4 things means sp3 hybrid for that carbon. Okay. So the other important thing is that each one of these bonds is an sp3 bond. Okay, each one of those is an sp3 orbital. That means that I have 4 sp3 hybrid orbitals. Okay, and they each directly overlap with the 1s of the hydrogen. The hybridization itself is why they orient in the 109.5 degree bond angles. Okay, ammonia. Remember, ammonia has a tetrahedral electron geometry, right? But a trigonal pyramidal molecular geometry. Right? So our bond angles are still about 109.5 degrees because that's determined by our electron geometry. Right? And we've got NH4 plus, so our Lewis structure for that would, it's NH3, my mistake. Ammonia, H3. Right? So again, determine how many areas of electrons you have. Let's change the color a little bit. So I've got 1, 2, 3, 4 areas equals sp3. Okay? So your molecular geometry does not determine hybridization. Okay? Let's make a note of that. Okay? The electron geometry determines hybridization. So you count the areas just like you would determining electron geometry. All right. Now let's start to take a look at how we can apply this to slightly larger things. Okay? So now we're not dealing with a single central atom, but just like we did doing geometries, we can look at individual central atoms. So let's take a look at and call this carbon number 1. Okay, this carbon on the left. how many areas of electrons are around that carbon, right? We have 1, 2, 3 areas around that carbon, right? So 3 areas means S, P, and P, or we call that sp2. Okay, so carbon number 1 is sp2 hybridized. Okay, and then we can look at carbon number 2 and it's exactly the same, so it's also sp2 hybridized. Now remember, sp2 has 1 unhybridized P. Okay, because remember we had 3 P's to start with. Remember we've got an S and we've got 1, 2, 3 P's. And if I take and combine 1 S and 2 P's, that means that I've got 1 left over that is unhybridized. Okay, and guess what? That unhybridized p orbital is what's responsible for that extra bond. Okay, and we'll get to that in a second with a better drawing. But let's take a look at this particular thing. So we have 3 central atoms in this molecule. I've got this carbon, and this oxygen. Okay, so let's take a look at the hybridization around each one of those things. All right, so our carbon on the left has 4 areas of electrons, so sp3. Okay, our carbon in the middle has 3 areas, so we call that sp2. Let's take a little this guy. Now our oxygen has 4 areas, sp3. Okay, so in case you're still trying to figure out areas, let's go ahead and sort of count those, go through counting those up. I'll use a green, lighter green this time. So talking about our carbon on the left, there are 1, 2, 3, 4 areas of electrons around that carbon. That's why we get 4 areas and sp3. So S and 3 P's makes 4 things, sp3. Our central carbon has 1, 2, 3 areas of electrons around it. So S, a P, and a P, that makes 3 things, sp2, and that will have 1 unhybridized p orbital to play with. And then our oxygen, remember, lone pairs count as an area, so our oxygen has 1, 2, 3, 4 areas around it. So S and 3 P's makes 4 things, or sp3, hybridization. Okay? All right, now, let's talk about how those unhybridized p orbitals come into play. So, ethylene has a basic Lewis structure that looks like this. And we kind of played with this this one up there a little bit higher in the slides. Right? So we decided that each of these carbons are sp2, right? Which means that we have 1 unhybridized. That should be a Z. Anyway, you know what that says. 1 unhybridized p orbital. Okay? And that is this right here. Okay? So each of these purple ones, these are all sp3, sp2 hybrids. Okay? And so when I look at the larger image of this molecule, these are the bondings of my sp2s. Okay? So each one of those bonds is an sp2 hybrid orbital doing its work. Okay? So sp2, 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 and so on and so forth. sp2, sp2. Okay? So all the sp2s are doing the direct orbital overlap. Okay, and that's right here, direct overlap. Okay, and when you have direct overlap, that means that you have what's called a sigma bond. Okay, so every time you have a direct overlap, you have a sigma bond. Okay, so let's sort of clean this up a little bit so I can talk about the next idea. Okay, so what happens is these unhybridized p orbitals, they are sticking up and down in the z-axis together, right? These are both sticking straight up and down, whoops, sticking straight up and down in the same axis, right? And so what you get is an indirect overlap okay, an indirect overlap of these p orbitals. Okay, and when you have that top and bottom, that creates a single pi bond. Okay, so let's take a look at what that sort of looks like. Okay, so over here, this plane, that's all of my sp2 bonding. Okay, that's all being done in the sp2. And then I've got these unhybridized p orbitals, and they're going to sort of, at a distance, share. Okay, so these are side-on interactions. All right? Remember, I'm going to come back up here. So over here, my direct overlap of orbitals makes sigma bonds. Okay? In these sigma bonds, they're actually physically overlapping each other, right? There's actual crossing of orbitals, right? But with my unhybridized p orbitals, they're not actually touching each other. They're not actually overlapping, but they're aligned in such a way that they can share their electrons over a distance. And so what we get is this sort of above and below thing, which makes one extra bond. Okay? Now it's kind of confusing, but you got to trust me on this, that when you get that overlap above and below the plane, you get a single extra bond, and we call that a pi bond. Okay, it's the overlap of unhybridized p orbitals. Okay, that's why we want to keep track of how many unhybridized p orbitals there are, right? So let's take a look at something more complicated yet. Okay, acetylene, if I were to draw the Lewis structure of acetylene, it's going to have a triple bond between the carbons. Okay, so what would be the hybridization of each carbon? Each carbon has two areas around it, so each carbon is simply an sp hybrid, right? So if they're sp hybrids, each one of those has two unhybridized p orbitals. Okay, so I'm looking at the diagram over here on the left, right? So you see your sigma bonds. Your sigma bonds, those are the SPs. Doing their bonding, their direct overlap. Right? So I have 3 direct overlaps. That means 3 sigma bonds. Okay? So then, to clean this up a little bit, and we'll use a slightly different color. Okay, so I've got 2 sets of unhybridized p orbitals. Each carbon has 2 unhybridized p's, right? And they are sitting right here. There's one unhybridized p, and the other one is in the, I guess, the y-axis or the x-axis. So that's sitting right there, and the other one is sitting right there. Okay, so we get direct or a sideline overlap right here, And then we get another sidelong overlap front and back. Okay, so our drawing in the middle is showing that top and bottom. So here's your top and bottom, and then here's your front and back. Okay, so what you end up with is sort of a sandwich, which makes two. We have two pi bonds. Okay. So if I have 3 direct overlaps, I have 3 sigma bonds. If I have 2 indirect interactions, I have 2 pi bonds. Okay, and there's actually, and so we're doing all this direct overlap, indirect interaction terminology, but it's actually a lot simpler than that to determine how many sigma or pi bonds there are. Okay, so counting sigma pi bonds, and I've got this wonderful sort of hideous molecule to look at. So easiest thing, so all bonds count for 1 sigma. 1 sigma bond each. Okay, so the first thing you want to do is just count up all of the places where there's a bond happening. Okay, and then so any extra lines count for 1 pi each. Okay, so let's take a look at our big ugly molecule here. Now the first thing I want to do is just count every bond. Count all bonds. Okay, I'm going to go through and say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so each place that something is connected to another thing counts for a sigma. So I have 17 sigma bonds in this molecule, provided I didn't miss any. Okay, so now I'm gonna back up here. Sigma bonds. See if I can delicately erase things to clean things up, especially in our double bond places. Double and triple bonds. Okay, so any place that you have an extra line counts for a pi bond. So we have 1, whoops, that's the eraser. Make that green. Right, so we have 1, 2, 3, 4, 5, 6 extra bonds. So that means that I have 6 pi bonds. Okay. So now let's take this another step further, and let's see if I can clean this up again. At least get rid of some of these extra lines. Let's take a look at hybridizations. All right. So just about all of the carbons in this ring, right? Let's look at the top carbon in the ring. Let's look at this guy right here. Right? So how many areas of electrons are around that carbon? And the answer is 3. So that carbon is sp2 hybridized. Right? 3 areas. Right? So the carbon just to the right of it, this carbon, 1, 2, 3, also sp2. This one is sp2, All of these carbons are going to be sp2. Okay, because they each have 3 areas of electrons around them. All right, let's come to the bottom of the ring and that branch that comes off of it, and let's look at this carbon. What is its hybridization? And it's got 2 areas of electrons around it, so it's sp. Okay, same thing with the carbon below it. This carbon is also sp because it has 2 areas of electrons around it. Okay, so moving to the right-hand branch off of the ring, the first carbon that we run into is this one, and it has 3 areas, so it's also sp2. Okay, the oxygen has 4 areas of electrons around it, sp3. Okay, so we can determine all kinds of things about molecular shape now, and hybridization, and sigma and pi bonds, all kinds of wonderful things. We have lots of information now. And that pretty much does it for valence bond theory. Now the next idea is molecular orbital theory. And molecular orbital theory is different from valence bond theory, in that valence bond theory is just talking about combining molecular orbitals, whereas valence bond theory is talking about combining all the electrons and all the atoms and everything together. Okay, so let's just talk about those contrasts. So valence bond theory combines orbitals only on the central atom. On a central atom. MO theory, molecular orbital theory, combines orbitals on all atoms. Not just a central atom. Okay, so lucky for you all, we're not going to get into large, complicated atoms and molecules here. We're going to be sticking to row 2 of the periodic table, and we're just dealing with diatomic molecules. Okay, so 2 atoms, each molecule. Now, molecular orbital theory can deal with much, much larger things, but boy, does it get complicated real fast, and you'll see how quickly things can go awry. All right, so, but let's talk about our most basic example, our simplest example, is dihydrogen. Okay, so the idea with molecular orbital theory is that I'm going to take and look at the orbitals that each of the hydrogen atoms has. Okay, so if I'm sort of drawing another thing that is looking at energy going up, I'm going to have 2 1s orbitals. There's one of them, and I'm going to combine it with another one, right? And we can call this hydrogen A and hydrogen B, right? Each of the hydrogens that are going to combine to make dihydrogen, right? So each one of these is a 1s orbital. And that gives me 2 molecular orbitals. Right? One from each hydrogen. So what's going to happen here is that they're going to combine in 2 different ways. Okay, so if I have 2 molecular orbitals, I'm going to get 2 combinations. Okay, and so what happens with one set is that the 2 orbitals will combine into sort of a homogeneous little blob, okay? And we refer to this one as a bonding orbital. All right, and we will, since we're dealing with 1s orbitals, we're going to call it sigma 1s, right? Because our bonding orbitals are sigma bonds, right? The other possibility is that they push each other away, right? So what we'll have is a node, and we'll have our things on the other sides, and they'll shove each other away instead of combining. Okay, and we refer to this one as an anti-bonding orbital. Okay, and we'll give this a sigma star 1s. Okay, so the star denotes anti-bonding. No star means bonding. Okay, and notice that the anti-bonding orbital is higher in energy, so it's less stable. Higher energy, less stable, right? And the bonding orbital is lower energy, more stable. Okay? So this is how molecular orbital theory differs from valence bond theory. Valence bond theory is talking about hybridizing and mixing orbitals and making new shapes. Whereas molecular orbital theory very simply shows us what kinds of bonds can be made, okay, based on combining molecular orbitals. So the common notation, so the most common way for us to show this is with what we call a MO diagram. Okay, a molecular orbital diagram. Okay, and the way I'm going to do this is I'm going to take, on one side, I'm going to have my hydrogen A and show that it has a 1s orbital with a single electron in it. Okay, and then on the other side, on the far side, I've got my other hydrogen atom, my hydrogen B. And we'll say that it also has a 1s orbital with a single electron. Okay, now between them, in the center, I'm going to show my sigma 1s and my sigma star 1s. Okay, so in here, I'm going to make these blue so that they're a little different. Slightly lower in energy, here's my sigma 1s, and then slightly higher in energy is my sigma star 1s. Okay, bearing in mind that this is all based on the idea that higher up is higher in energy. Okay, and I'll have these little sort of guidelines. Okay, now what I'm going to do is I'm going to take my electrons from each side, so I've got 2 total, right, 1 from each atom, and I'm going to fill from the bottom. Right, and I have to follow Hund's rule in my filling. And this will make more sense when we do larger things. Okay, but since H2 is so simple, it's hard not to follow Hund's rule, right? But what I'm not going to do, so violating Hund's rule would be to take 1 electron and put it here, and the other electron to put it there. Okay, can't do that, right? Hund's rule says that I have to fill singly and then double before I move to a higher energy level. Okay, so following Hund's rule, I'm going to take and put my second electron there. Okay, so I have to fill a particular level before I can start putting electrons in the next level. Okay, but on the same level, I'm going to fill them singly before I pair them. Right, and like I said, that will make more sense when we do more complicated molecules. All right, so let's take a look at bond order. Right, we talked about bond order once before, But we have a slightly new way to look at it. So bond order, when we're dealing with molecular orbitals, is 1/2 the bonding electrons minus the antibonding electrons. Okay, so in our case, sigma 1s, those are the bonding electrons, right? And the star are the antibonding. Okay, so my bond order for this molecule, 1/2, I have 2 electrons in the bonding minus none in the antibonding, means that I've got a bond order of 1. And if you remember, a bond order of 1 means that I have a single bond. Right? And that's what we would predict. That's what we've, seen before. That when we draw molecules of hydrogen, dihydrogen, they look like this, right? And so we would expect there to be a single bond. So let's see what happens. Let's play around a little bit. And that's kind of the fun aspect of molecular orbital diagrams, is we can try things that really shouldn't exist and we can show why. So let's take a look at what would the MO diagram be for H2 2+, right? So that means that each hydrogen atom should have 2 electrons, or excuse me, 2 minus. What am I saying? H2 2 minus. Okay, so I'm gonna start with, on one side I'll have hydrogen A and the 1s, hydrogen B on the other side, it's 1s. Okay. And in the middle, I'm gonna have slightly lower in energy, my sigma 1s and my sigma star 1s. Now each of these, since it's H2 2 minus, each one of the hydrogens should have 2 electrons. Okay, so I'm going to take, I've got 4 total to play with, 4 total to put in my central part of my drawing. So I'm going to fill from the bottom first. Fill from the bottom. So I've got 1, 2, 3, 4. Okay, so I take my total from the outsides, total number of electrons, and I put them in the center of my drawing. So let's look at the bond order. 1/2 the bonding minus the antibonding. So I've got 2 electrons in the bonding, and in this drawing I've got 2 electrons in my antibonding, which means a bond order of 0. Right? Bond order of 0 means that this shouldn't exist. Cool, huh? So we can demonstrate, right, based on this bonding theory. Right now, ready for your minds to be blown? I thought you might be. So larger molecules. All right. We could show how things go together using every orbital that these things have. But things only matter with the valence shells. So when you're doing these larger molecules, use only the valence shells for your MO diagram. Okay? So we're only dealing with, in this class, we're only dealing with row 2. So we're dealing with 2s and 2p. Okay? So let's do a MO diagram for N2, dinitrogen. All right, so on the left side, I'm going to have nitrogen A, and on the right side, I'm going to have nitrogen B. All right, so there's 2 nitrogens in my molecule, so nitrogen A and nitrogen B. So nitrogen A has, at its lowest level, a 2s, and then it has 2p, which has 3 p orbitals, right? The other nitrogen has the same thing, so about the same energy it's 2s, and it's 2p, and the p has 3 slots, right? So each nitrogen has 5 valence electrons. So we fill our valence shell 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay? So now, we've already sort of dealt with the S part, so with our hydrogen. So the only difference here is that we're dealing with the 2s instead of the 1s, but the idea is the same. So I'll have my sigma and my sigma star for 2s. All right? Now dealing with the p's, things get a little bit more complicated. So my first level dealing with p orbitals is a pi. So I'm going to say pi 2p, and the pi has 2 slots. The next slot up is sigma 2p, and then the next slot up is my antibonding pi 2p. It also has 2 slots. And then at the very top, we have a sigma antibonding sigma star 2p. That doesn't say 2p. And it has a single slot. Okay? And same deal here. This whole section goes with the p's. Okay? So, looks pretty intimidating, right? But it's really not. The only trick is remembering the order of how things are arranged in the p section, and we'll talk about that here in a second. But I have 10 electrons total to put in the center of my drawing. So I'm going to start at the bottom, and I'm going to fill from the bottom up using Hund's rule. Okay? So in my 2s, I've got 4 to play with, so I'm going to put my 4 electrons in there. So 1, 2, 3, 4. That takes care of all of my s electrons. Okay? Now in my p level, I have 6. Right? So I'm going to follow Hund's rule and the Pauli exclusion principle. So I go 1, 2. Notice I didn't put them both in the left hand, even though I could. I want you to pay attention to this. Fill them singly before you pair them. So I've got 6, 1, 2. Now I can pair them 3, 4, 5, 6. Okay? And the number of electrons in the center of the drawing should match the total number of electrons between the 2 atoms. Okay? So this is how we do an MO diagram for larger molecules with more valence electrons. Now let's take a look at the bond order just for fun, because I think you'll find it interesting. So the bond order is 1/2 the bonding minus the antibonding. So let's take a look. Our bonding orbitals are anything that doesn't have a star. So I've got 2, 4, 6, 8 bonding electrons, right? And then I'm going to change up the color just for fun. And then my antibonding is anything with a star, right there, right? My sigma star 2s is the only antibonding orbital that has electrons in it. So 8 minus 2, so 1/2 of 8 minus 2 equals 3. So guess what? Triple bond, right? And if we draw a Lewis structure for dinitrogen, guess what we get? We get a triple bond. All right? So when we're dealing with these larger molecules, there are 2 different arrangements of our MO diagram. Okay, what we get is one arrangement for B2, C2, and N2. And we get a second arrangement for anything larger, so O2, F2, or Ne2. Okay, so let's take a look at what are the differences, right? So if I draw, so we just did the one for N2, so I can go ahead and put that one down. So starting from the top, because it's easier that way to make sure everything is lined up. I had my sigma star 2p, and then I had my pi star 2p, and then I had my sigma 2p, my bonding, and then I had my pi 2p, and then below that was the sigma star 2s and my sigma 2s. Right? Okay. Now, when we get up to the oxygen, what happens is that nitrogen, we have a half full p orbital, right? Which is very stable. And then when I get to oxygen, I've added one extra electron to that p orbital, and I've changed the energy of the p orbitals, okay? So that's going to affect the arrangement in my MO diagram. So let me go ahead and just put this in here. So the sigma star 2p is in its normal place, as is the pi star 2p. But here's where it gets different. The next level down is now my bonding pi, followed by my bonding sigma. Okay, and then the S is the same. Right? Right, so where things get a little bit different, depending on what molecule you're making, is these places are flipped. Okay, and again, the reason for that is that your nitrogen 2p is half full, which is stable, right? Pretty low energy. And then when I get to the oxygen, when I go one more step up, the 2p has one more electron in it, right? Less stable, more energy. Okay, so that's why the MO diagram flips when you get above nitrogen. Okay, so you want to be aware of that when you're doing mastering and when you get to the exam. Okay, so let's do one more MO diagram before we call it a night. All right, let's do an MO diagram for something that's not homonuclear. Right, let's do a heteronuclear MO diagram. Let's do a diagram for NO. Okay. So I'm going to take and put my nitrogen on one side and my oxygen on the other. And I'm going to do my MO diagram to accommodate the oxygen, right? Because I just told you that they flip when you get high enough. Right? So my 2p for the nitrogen is sitting there, and then my 2p for the oxygen is going to be slightly higher in energy because it's got more stuff in it. Right? And then we have down here our 2s, and probably about the same energy is the 2s for the oxygen. Right? So let's construct our diagram. So at the top here, I've got my sigma star 2p, and the next one down is my pi star 2p, and then my bonding pi, and my bonding sigma. Okay. And then down here we have, of course, the antibonding 2s and our bonding 2s. All right, so let's put in our electrons for each side. Nitrogen's got 5 valence, so we're going to say 1, 2, 3, 4, 5. And our oxygen has 6, so let's put those here. All right, so now let's proceed to pack our electrons into the center of our drawing. So in the 2s level, I've got 4 electrons to add to the drawing. So I'm going to say filling from the bottom. There's 4. Now in my p level, I have 3 from the nitrogen and 1, 2, 3, 4 from the oxygen, so that's 7 total. So I'm going to fill from the bottom. So 1, 2, 3, 4, don't pair them yet, 5, 6, and then we move up to 7. Okay, so let's take a look at the bond order, because this will be interesting for you. Bond order, 1/2 the bonding, which we have 2, 4, 6, 8. All right, so 8 electrons in the bonding, minus the anti-bonding, which we've got 2. Let me come up here to the top. There's a third. So 1/2, 8 minus 3. 8 minus 3 is 5. So I've got a bonding order of 2.5. So what that tells us is that our bond is between double and triple. Right, so we've got some kind of like funny hybridization going on, or funny bonding. Okay. So it's an interesting thing. Now, here's the last thing that I want to talk to you about. Is this molecule paramagnetic, or is it diamagnetic? Okay, so remember, para is unpaired, right? So let's look in our MO diagram, and sure enough, I have an unpaired electron right there. Right? Everywhere else in this diagram, the electrons are paired up, right? So is it paramagnetic? The answer is yes. Right? So NO is weakly susceptible to magnetic fields. Right? So let's come back up and take a look at one of our other MO diagrams and see if we can decide paramagnetic or diamagnetic. So let's look at dinitrogen. Right? Do we have any unpaired electrons? All of these electrons are paired up. So the answer would be that dinitrogen is diamagnetic. All paired. Okay, so that pretty much does it for us in this chapter. We've covered molecular geometries, we've covered valence bond theory, we've covered molecular orbital theory, and all kinds of wonderful things.